Okay, we are recording. Um, okay. Now, today's my birthday, so please try not to add to my gray hair count. Although I thank you.
Give us the day off. Take your time.
Yeah. But the 6 people not showing up is not helping matters. But okay. Now, or should I say the 6 unexcused absences? Um, okay. Now, I guess first things first. How is the homework coming? Okay. All right, that's good. Because 5 out of a zillion. Now, one thing I wanted to, well, I hope there'll be at least some specific questions, but one thing I want to make sure that everyone's aware of, if you look at the assignment, because of course there's explorations like last time, but don't forget these. These are at the very end of a chapter. So after the explorations, concept check, and so forth, there's exercises here. I only assigned the first 6. So I hadn't got any. I got questions on just about everything else, but not this. So I just want to make sure that didn't fall through the cracks. Of course, there's, like I said, a zillion problems altogether. So, so forgetting these wouldn't actually do too much damage. But okay, I guess this is where I remind you that each overall homework assignment, so each chapter's work, counts for a meager 4% of a grade. So, so a few problems here and there won't hurt you too much, but I may, as the semester goes on, have some like bonus opportunities, something like that. I'd like to do that, but maybe sometimes too much. But we'll see. Okay, now. So now, it seemed like most of the questions that were asked last time dealt with section 2.1. So I'm hoping that more people are starting to get into the 2.2 stuff on floating point arithmetic. So yes.
Just a general question about 2.2. When you said if we ask questions, we can get out of the certain problems, that was for the concept.
That's for a concept check. Right. Yeah. There's no getting out of those. Yeah. Okay. Yeah. All right. Next.
How do we know?
What?
How do we know?
Oh, if you're exempt?
Yeah.
Yeah, that was actually my next point. I do need to go back through my emails and let people know, because very early on I was doing that, but I haven't been so good about that lately. But don't worry, I have everybody's questions, so you'll be hearing from me within the next day or so.
Does going by your office count?
Yes, that counts too.
Okay.
Yeah. Okay. So I think we could actually have a fair number of people who will be exempt. So if you haven't done those yet, and you have contacted me, then hold off for a bit. Okay. All right. Sorry, I haven't been as up on that as I was at the beginning. Okay. So are there any problems that anyone wants to bring up? Really? You guys are planning to ruin your weekends by... Yeah, I guess it makes sense, because I'll be ruining my weekend by grading homework 1. I meant to get that out of the way this week, but I just wasn't feeling it. So, and I guess this is going both ways, right? Yeah. Okay, that's fine. So we'll all be in misery. That's good. That's how you start fall. Okay. Let's see what else about. Okay. So, um, so, so since there aren't any questions, I didn't expect to have this much time, class time available for whatever else I wanted to do. But that doesn't necessarily mean I'll end early because I can yammer on like anybody else. But um, if not more so. So one thing that I want to um, make clear, since next week is when homework 2 is going to be due, and then we'll be transitioning into chapter 6 that you see here, and so and that of course that assignment's not due for a while. It's due October 17th. So you have a fair amount of time. Let's see. Well, yeah, a little less than a month from today. But and that's actually the Tuesday before fall break. So really, yeah, if you turn in homework 2 on time, you'll have 3 weeks. Now, look how many problems are here. Again, there's a zillion. Now you can get exempt from at least from some, or if you ask a lot of questions, even all of these. But it still leaves 1, 2, 3, 4, 5, 6, 7, 8, 13, 17 explorations and 6 exercises. I suggest divvying them up accordingly amongst the time that you have. So that, because if you let this wait till the last couple days before, those will be the worst days of your life. I promise you that. So I hope that you guys aren't ruining your weekend too badly by finishing up homework 2. But there's the usual habit of taking so long to get started is is really not going to help, because you want to make sure that you don't let this spill over too much past the due date, because the week after this, October 24th, that's the midterm. And that last Tuesday before fall break is I'll be using that class period to do review. I will have, like in the next couple days or so, the practice test up. I gave you a glimpse of it last time from the old site. There will be some adjustments to it, but what you saw there was pretty much what the practice test is going to be. So as we finish up chapter 2, get into chapter 6, especially as we cover sections, when it's all fresh, what I urge you to do, and again, just common sense. Take time sooner rather than later, at least to look at the explorations. Because if I've just covered, say, section, say 6.3, which is what I will be covering next week, and you go look at that part in the book, and you look at the explorations or the exercises, and you can't even understand what's being asked, which could be due to 2 things. Either you didn't digest that enough, or maybe I wrote it that badly. It could be either one. Either way, we want to get that cleared up. So, and even if you don't really have the time just yet to really dig in and try to do these, if you could at least look at them, and based on having just seen this material covered here, or reading through it on your own around that time, that at least you have some idea of what this is about, what the question is asking for, so that when you, because if there's things about the questions that are unclear, like how I've worded it or whatever, or God forbid, especially if there's a mistake, I really want to nip that in the bud quickly. So please help all of us out, and don't wait so long before digging into those. Because as I get questions, I'm updating the text almost daily. Usually just to take what's already there and just clarify it a bit, like maybe reword things a bit. So in fact, if you go to where the book is posted on the resources page, and I can't believe it forgot the password again. Okay, yeah, but it's today's date. So actually, very late last night, I'd done some touching up on it. So, so you want to keep that fresh because maybe you'll get a more clear wording of certain problems than there was before. But at least you can tell by this when I was last messing with it. Okay. So now, whoops, don't need that. Okay. So, are we sure we don't have any problems, specific problems we want to bring up at this time? Bless you. Okay. Or there might be one, or
Part of the book should we look at to get a better idea of how to do it?
okay, number this one.
Yeah.
Oh, okay. Well, really, this so this is really a MATLAB exercise. So what you can do is, if you so now, another thing I want to point out about these problems in general, because what I actually put in a problem in terms of like details is what I generally care about. If it's something I don't specify, that means I really don't care. For example, I don't really care what the value of n is. You can pick that. If you want a suggestion, I'll give it to you. Like maybe let's just say 100. So in other words, 101 equally spaced points in this interval. So the idea is what you do in MATLAB is if you go ahead and create a vector of n plus 1 points, equally spaced points, but you do it in two different ways using so in one case you're always adding the spacing to the previous point. So you'll start with 0, then you'll have h, then you'll add h to that, then add h to the next one, add h to the next one. You'll just keep adding h a zillion times to get all the points. Or the second way, using multiplication. So taking the index and multiplying that by h. So so this is a little for loop exercise in working with vectors, things like that. So the idea is, so when I actually tried this with computing this vector of points, because mathematically you can see that what you are supposed to get is equal. That both of these will generate that vector of equally spaced points. But what you're going to actually see when you do this yourself in MATLAB is different. And to try to explain why. Now, as for why, that deals with the last portion of this chapter, issues in floating point arithmetic. So this is combining material from two different parts for this. One thing I want to point out that related to this problem here, we're performing addition in this case and multiplication in this case. Now I'm going to let you see for yourself when you compute this vector two different ways, which one is the more accurate. But regardless of that, the first way is the more efficient. Because this is doing an addition each time. This is doing a multiplication each time. Multiplication and division are more expensive operations than addition and subtraction. And in fact, division is somewhat worse than multiplication. And the funny thing is, back in the really, really old days of computers, back in the 50s, 60s, and so forth, programmers were more careful about these things. They knew that it was more expensive to divide by 2 than multiply by 1/2. and they actually paid attention to those things. These days, not so much anymore, because you feel like everything's fast. But these things that were true back then, in terms of what's faster than what else, is still true today. Which also reminds me that I guess because of how technology has advanced, it's allowed programmers to get a lot more careless than they used to be. So at my undergrad institution, Purdue, before they even had a computer of their own, they had someone working there who was a driver/operator. So what he would do is go around to all the faculty or researchers at the end of each day, pick up their programs like were specified in like punch cards, drive up to the University of Chicago, run the programs on their computer, gather the output, and then distribute that to the users in the morning. Can you imagine if you made a mistake? Think about how many mistakes you've made in the code you've written for homework 1. Yeah, game over. I mean, it's just, yeah, it's like we'd all just get fired. And I guess a more modern day example of this is one of my fellow PhD students at Stanford. He, for his dissertation research, he had all his code written out, and this is like a significant application of reams and reams of paper, all written on paper. And it was just a few weeks before he was supposed to finish and graduate. And so one of his office mates said, like, oh, shouldn't you actually type that into MATLAB and actually run that? And he's like, oh yeah. So he just goes ahead and it works the first time because he was that careful. So I wish I could say I was, but no, I'm not. Okay, but my first programming teacher, so I guess the equivalent to CSC 101, but it was Pascal, not C++, because C++ had only just been invented recently, said that the sooner you actually start writing code, the longer you're actually going to take doing it to get it to work. That, in other words, take more time up front to think about what you're doing before you actually start typing things in, or you're going to be fixing mistakes, spending so much time fixing mistakes. I actually write out, you see, I put comments all the time. I write the comments first, so I can understand in words what I'm supposed to be doing, and then just try to break it down from there. And I found that helps me to come a lot closer to getting things right the first time. Okay. Any other questions on problems? Last chance, I swear to God. Okay. All right. Now, yes. Yeah. You know, it was about 4 or 5 years ago. I was in my Angry Birds phase. You may have seen him in my office, behind me on the bookshelf, and so I would have them in class so I could throw at students like yourself. Yeah. So. Okay, but at some point I just got bored of playing, and then there was my Candy Crush phase, and that's gone too, and nobody wants to play Words with Friends with me anymore. So, I can't imagine why. Okay, so one thing I just want to try a little experiment on you guys is so now that we're almost actually we are a little more than a month into the semester. So if you were to summarize what the class is about, content-wise and so forth, in just one sentence or in just a few words, what would it be? I'm just curious. Like, if you were to sum up what this class is about, based on what we've seen so far, briefly. Okay. All right, good. That certainly captures a good chunk of what we've seen. Anyone want to throw out anything different? Really? No?
Analysis, or this type of analysis is about getting an approximate answer, not always the exact.
Mm-hmm. Okay. This exercise was sparked by a student saying that they weren't really sure what the class was about at this point, or I guess trying to nail down what it's about. Okay. So I just want to kind of take you guys' pulse on this. Anyone want to throw out anything else? Okay, so you're pretty much in general agreement, or okay, or you just don't care. But all right. Okay, and certainly, there's definitely accuracy in these things, especially when you take the union of them. I could also see if you thought it was basically a course about MATLAB because we spent so much time on that, and we're going to see quite a bit more of that before we're done. Although MATLAB will still end up not really only being a relatively small portion of your grade. Now, and the thing is, but even though these comments accurately reflect what has been covered so far, it doesn't really capture what the course is meant to be about as a whole. But we're only about a quarter of a way in. And so my goal today is to actually adjust this viewpoint a bit by moving forward into the next thing. Now, what you're going to see during the rest of today is there is going to be overlap with what Dr. Chen covered while I was away, but it's been my experience here that there can never be too much review. So, but also I'm going to be giving a somewhat different viewpoint than he did. Now, okay, so let's get back to this central question. Why are we here in this course? Now, of course, you can tell me it's a requirement. Actually, it really wasn't much of one when I started here. We didn't have this whole technology requirement thing. That was added later, but really did wonders for enrollment. Okay, and that is solve whatever variety math problems that we could by hand with the aid of computers. But the trade-off, as mentioned in Kristen's point, approximately instead of exactly. And now, and then because it's computers, then there are a lot of issues with using computers and because of computer arithmetic, and it goes to a point that that Jade was making, that we have to have a thorough understanding of that too. Okay, now, so to get started down this path of actually being able to solve problems, well, first of all, what problems? And there's a lot of problems that we're going to solve in this manner. Although we're only going to see certain ones this semester, and then those of you who want to carry on into the second semester, which in recent years, like however many take 460, I guess about half those continue on into 461. But if you do, then you would see additional problems, really more elaborate ones tackled from there. So I'm just going to mention a couple that are of great importance this semester that will also continue to be important next semester as foundational ingredients. What about problems that you're used to solving already from calculus? derivatives and integrals. That would be a very good starting point, because if you can handle derivatives and integrals, then you can get into differential equations, and also nonlinear equations. Root finding can also be helpful, because derivatives play an important role in that. So I'm going to focus just on this narrow but fundamental sphere of problems, derivatives and integrals. So I'm just being able to do calculus approximately, but for more problems than we could before, more than you were confronted with in Cal 1 and 2. Okay, now, so the thing is, there are two questions that I'm going to put out there for how we could get a start on being able to compute derivatives and integrals for functions that are impractical to handle using the techniques we learned by hand, or maybe even impossible. So, so two issues. We can only handle certain functions by hand. And the second thing is we're limited by the capabilities of a computer. Now, of course, computers can perform so many operations so quickly, but there are only certain operations, bless you, that they can readily do. And so I keep coming back to this: add, subtract, multiply, divide. So, so now, if I were to ask pose this question, are there functions that are easy to differentiate or integrate? Well, actually, you tell me. What functions, what types of functions are particularly easy? What? Can you narrow it down more? Easiest one of all. Okay. All right. In between. Polynomials. Yeah. Okay. And then the second question is, what functions can be evaluated exactly, I should say, except for round off? There's no getting around that. Using only the 4 basic arithmetic operations. Well, what kind of functions you've seen, like in calculus, for example? It's the same, yeah. So again, polynomials. That suggests we take a look at polynomials. So what we can do, so the approach so where this is going, and this is going to unfold over quite a while, so I'm going to have to keep coming back to this to remind you guys as we go down the rabbit hole of working with polynomials, is how to compute derivatives or integrals numerically. So it's a two-stage process. First, you approximate, because when you're computing a derivative or an integral, you're dealing with some particular function. There's a function you're taking a derivative of, or there's a function at f of x that's your integrand for your integral. So you're approximating your f of x with a polynomial of some kind. And really the point of the next few weeks is to have a clear understanding of what is the best way to do that. Best meaning a lot of things. Accurately, efficiently, robustly. So in other words, not in a way that's too sensitive for round-off error, things like that. And then, because, so we're doing this because, number one, computers can work very nicely with polynomials. And then, solve whatever problem you're dealing with, whether it's a derivative or an integral, exactly on the polynomial. Because that's something that a computer can very easily do. If you have a well, the thing is, MATLAB has these functions already, polydir and polyint. You give it a row vector of coefficients, and it will spit out, these functions will spit out the coefficients of a derivative or the antiderivative. And then you can use polyval to evaluate those at whatever points, like to compute a derivative at a certain point, or compute a definite integral over some interval AB. Okay, so this is the approach that almost the rest of this course, except for like the last few weeks, as we get close to Thanksgiving, is going to take. We're going to be focusing on derivatives and integrals. More time on integrals because they're a lot harder. And for that purpose, though, we need a good way of approximating functions by polynomials. So to give some context, why we need what we've seen so far, because it seems like I'm taking a rather sharp turn here. Of course, we're going to be implementing everything in MATLAB. Okay, of course. And the other thing is if we're going to be approximating f by a polynomial, then we need a clear understanding of how accurate that approximating polynomial is. And if we have an understanding of that error, then how does that affect the error in your derivative or your integral? So, in other words, the backward error is error in approximating f by a polynomial. So chapter 6, we're going to learn how to measure that error. The forward error is the error in the derivative or integral of f. So we're going to have error formulas for both of these things, for backward error and forward error. If you have backward error and forward error, what can you infer from that? Condition number is what relates it to. Very good. So then we're going to see which problems are between approximating derivatives and integrals, which of these problems is ill-conditioned and which is well-conditioned. And the thing is, derivatives and integrals, those are, in a sense, inverses of each other. So you'll be right in thinking that one of these problems is ill-conditioned and one is well-conditioned, but as for which, you'll just have to wait and find out, or you can take a guess, or you can read ahead. Okay, so that's where all this error analysis is going to come into play as we go along. Okay, so the funny thing is, I said on the first day, what is the point of numerical analysis? To be able to solve mathematical problems on a computer and more generally than we could on paper, and yet we don't even get to actually do that until about halfway through the semester. So that's one of the unfortunate things about a course like this. There's a ton of ramp up, and it's unfortunate that it takes that long, but what can you do? That's the subject. Okay, so with that context, we have polynomial approximation. Okay, so this is chapter 6 that Dr. Chen started to get into, but now at this point, since you guys don't have any questions on homework 2, I'm really going to get into. Okay, and I understood he wasn't feeling well the second day, so that was unfortunate. What? Oh yeah, he told me that too. Yeah. Speaking of which, Ross, are you still the only one down there?
Yes.
Okay. Just want to make sure my attendance is accurate. Okay. Now, there's one very limited scenario in which you already know how to approximate a function by a polynomial. It's something you would have picked up around dealing with algebra or thereabouts. So what you know how to do is, given 2 points, x0, y0, 2 points in the plane, x1 and y1, find the equation of a line. That passes through those points. And how do you do that? You've been helping math zone students, some of you anyway. Yeah, point slope form. So what is the slope? Oh, yeah, okay. Yeah, unfortunately I switched notation to you guys because of what I'm doing later, but yeah, that's the idea. Okay, and then, point slope form, y minus y naught is equal to m, x minus x naught. Okay, so now if I write this out in full, so I'm going to call this p1 of x, p for polynomial, 1 for degree 1, it's just a linear function, so that would be y naught plus m, which I'll write out in full, y1 minus y naught over x1 minus x naught, times x minus x naught. Okay, now that's all fine and dandy, and of course chances are you might have needed to write this in slope-intercept form, y equals mx plus b, but we're not going to do that. The form that it's written in now is not conducive to trying something similar at higher degree. Because if you have 2 points, we just seen we can fit them with a line. If you have 3 points, then you can fit with a parabola, 4 points of a cubic, and so forth. So in general, n plus 1 points you can fit with a polynomial of degree n. So what I'm going to do is rewrite this. I'm going to group by y value. So in other words, I want to write this in the form of p1 of x is equal to y naught times something plus y1 times something else. So we just go ahead and do the algebra here. So what do I have multiplied? I have y naught sitting here, and then I have minus y naught times all this. So I'm going to gather all that. So I have y naught times 1 from the lone y naught term, and then I have minus, and then I'm going to have x minus x naught over x1 minus x naught, and then plus y1, and that is multiplied by all this again, x minus x naught over x1 minus x naught. Okay. Now, that first term involving y naught is kind of a mess, so I want to clean that up, and that means putting everything over a common denominator. This 1 here I'm going to write as x1 minus x naught over itself. So now I'm going to have x1 minus x naught minus x minus x naught all over the denominator. And then the other term is just fine the way it is. Okay. And now I can simplify. I have the x naughts canceling out. And then, so then I have x1 minus x. But what I'm going to do is I'm going to write it more like this. I'm going to write it as x minus x1, which I can do as long as I negate my denominator. So it's y naught times x minus x1 over x naught minus x1, and then this over here. Actually, I'm going to, okay, I want to put a little space there. Okay, so this is my equation of my line, but now written in a very different form, where we have a linear combination of your y values. So notice this polynomial here is also of degree 1, and so is this one. And they have nothing to do with the y values. They're multiplied by the y values and added afterwards. So let's take a look at this function right here. I'm going to call it L0. So that's x minus x1 over x naught minus x1. Okay, now let's take a look at what happens. What if you substitute in x naught? What do you get? So if you said x equal x naught, you get 1. All right, and what about if you substitute in x1? Yeah, well, that worked out pretty nicely. So in other words, if you plug in x naught, this becomes 1, and you get y naught for this term. But if you plug in x1, you don't want y naught at all. You want no piece of that. But it goes away. So similarly, if I call the other this part L1, well, first the general form. Okay, so then if I plug in x naught in here, yep, and then if I plug in x1, anyone? What? No. Yeah, you plug it in for x. Yeah, yeah. So you get x1 minus x naught over x1 minus x naught, and you get 1. All right. Does everybody see this? So the idea is, the way you can create a polynomial that's designed to hit certain y values that's prescribed x values is you make polynomials like this that are equal to 1 at the point you want and are equal to 0 at the point you don't want, that has a way of selecting the correct correct y value. So L0 and L1 are examples of what are called Lagrange polynomials. Not to be confused with Legendre polynomials, which we'll see later. There are a lot of famous mathematicians named L. I still hope to be one of them someday. Okay. Now, sorry, I couldn't resist. So let's. So now, this form is something that we can readily generalize to higher degree. So let's consider find a quadratic function passing through 3 points: x naught, y naught, x1, y1, x2, y2. So the form, so this is called the Lagrange interpolating polynomial, is, I can call it P2 of x because it's second degree. So we have y naught times L0 plus y1 times L1 plus y2 times L2. The idea is now we're prescribing this form in advance, and now we need to figure out what's going to make that actually work. What will be the correct L0, L1, and L2. So L0 needs to have these properties. If we plug in x0, we want y0 at that x value. So that should be 1. If we plug in any of the other points corresponding to y1 and y2, we must get 0. Okay. Now, what does that mean? I've specified that this is a second degree polynomial. Second degree polynomial can have at most 2 roots. Now I've just specified what the roots are. So L0 of x must be a multiple of, well, actually, I'll just write this out as an equation. It's equal to some constant, which I'll call c, times x minus x1, x minus x2. So x1 and x2 have to be the 2 roots of this polynomial. So in other words, this has to be the factorization. Now I can multiply that by whatever constant I want, and the job of that constant is to satisfy the other property, making sure that this condition is satisfied. Because if I plug in x naught here, I'm not going to get 1. So if I plug in x naught, I get c, and then I have x naught minus x1, x naught minus x2. And that has to be equal to 1. But now if it tells me what c is, I can just divide. X naught minus x1, x naught minus x2. And now I can say what the polynomial is. So this first Lagrange polynomial is, actually I can write it in this form. X minus x1 over this factor, x naught minus x1, times x minus x2 over x1 minus x2. Okay, so what I want you to do now is look closely at this formula and see what patterns there are in it. Which x values go where? Where is x? X is your one and only variable. Everything else is a constant. To convince yourself that it actually satisfies the 3 conditions. That if you plug in x naught, you get 1. If you plug in any of the other x values, then you're going to get 0. Does anyone have any questions about how I got this? If we look at the next one, L1 has to satisfy these 3 conditions. Plug in x0, you get 0. Plug in x1, you get 1. Plug in x2, you get 0. Now, my challenge to you is to keep in mind what we got for this formula given these conditions. Now you have these conditions. Can anyone tell me what I should put here? Yeah, x minus x naught is a good start. Okay. X what? Okay. X2. Okay. Oh, hold on. Ah, dang it. Sorry, hold on. I just realized a mistake up above. L0 should be x naught minus x2. That was a mistake. Okay. So I'll edit the diary on that. Just so you can see, this was correct. I just forgot to, I transcribed it incorrectly down here. Okay. L1, x minus x naught. Okay. So now this guarantees that the first condition will be satisfied. Okay, so what do you want to go down here? X1 minus x2. Now, we are going to need this, but it's an odd place to put it. What are you suggesting, Jesse?
That instead of x2, it needs to be x naught.
Yes. So x1 minus x. Because now, if you substitute in x equal x1, you're going to get 1. At least with what we have so far. Okay. Now, how do you complete it? All right, because the first 2 conditions so far are satisfied. We got to make sure it's equal to 0 at x2. Look at how L0 met that goal.
X minus x2.
Yes. That okay, so now that will guarantee that it satisfies this condition, and the first condition is still satisfied. This one no longer is. So how do you ensure that?
Over x1 minus x2.
Now you have the x1 minus x2. Okay. All right. Now, let's see if you can arrive at the third one, the third and final one. See if you're starting to get the hang of it. So we want it to be equal to 1 when we're at x2, but at the other 2 points, it's got to be 0.
X minus x2.
No. That'll make it 0, not 1.
X minus x naught.
Yes. All right, so now the first condition is satisfied.
Over x2 minus x2.
Yes, x2. Okay. And now the third condition for the time being is satisfied. So this second condition is what's left.
X minus x1. X2 over minus x1.
Yeah, x2 minus x1. Yeah, so now, so plugging in x0 or x1 will trigger one of these linear factors up top to be 0, thus making the whole thing 0. Substituting x equal x2 will cause cancellation of a factor right below it. So that's how these Lagrange polynomials work for any degree. Okay. Now, okay, so what I'm going to do at this point is I'm going to make up some data here. Let's see. So I'll make x equal to column vector 1 through 3. So I'm going to use polyfit with these x values, and I want for L0, I want so you can think of I'll fill that in here. So x0 equals 1, x1 equals 2, x2 equals 3. So then L0, using polyfit, which is how MATLAB handles polynomial interpolation. So with y values for this, I wanted it equal to 1 at this point and 0 at the other 2 points. So my y values would be 1, 0, 0. And the third argument you specify is the degree of your polynomial. And that is going to be degree 2. It should be 1 less than the number of points that you have for methods that we're seeing in this class. And, okay, so these are the coefficients of a polynomial. But it's not the coefficients I really want to call your attention to. It's the graph. So I'm going to make a bunch of x's from, let's say from 0 to 4. But I want some spacing. I want a lot of points between 0 and 4. Make sure I don't have any figures. So I'm going to plot against x the values of this polynomial at these x's in blue. Okay. What? Oh, I forgot to specify the polynomial, L0. So polynomial is the first argument. Your x values are the second argument. Okay, so there's our graph. But doesn't mean much just yet, but I'm going to fill in some more here. Now, I want my second Lagrange polynomial, same x values, but I want it to be equal to 1 at the second point. So now I'll hold on and plot that in red. Okay, and we see the graph here. and then finally L2, I want it to be equal to 1 at the third point and 0 at the other two. And I'll plot that in black. Okay, so now we have these three polynomials, but to show you their effects, I'm going to indicate on the x-axis these x values. So I'm going to plot at these my x values, which is 1, 2, and 3, all zeros, and I'm going to use red circles. So now we see, notice all the polynomials pass through these points. And I'm also going to plot ones, so you can see these points too. So notice the first polynomial, actually I'm going to label these. I'm going to use this command, well actually I'll use a legend. L0, L1, whoops, L2. So you can identify by color. Oh, I need to make that a little bigger. It's going to be a but again. It's supposed to let me select this, but it won't let me do it. I'm not sure why. Okay. No. Stop it. Okay. Bye. Okay. So never mind that. So the first one, L0 is blue. So it's equal to 1 at the first point, and look here, it's equal to 0 at the other 2 points. And then the second polynomial, it's equal to 1 at the second point, 0 at the other two. And then the third polynomial in black, equal to 1 at the third point, and 0 at the other two. So these Lagrange polynomials, when multiplied by the y values, will construct the polynomial you want to pass through the 3 points that you prescribe. Okay. So the general form of Lagrange polynomials for the n plus 1 points, x0, x1, x2, up to xn, therefore they have degree n, is each Lagrange polynomial, L sub I, is first the numerator. Well, I'll do this same form as before. So, okay. So as a product, for j not equal to I of x minus xj over xi minus xj. Now this is written in more neatly in the notes, or like in the book, and I'll take you to there. Chapter 6. Okay, so here is the general formula, equation 6.1 of the Lagrange polynomial, and and that's what we see here, is that this Lagrange polynomial degree n for point j, we want it to be equal to 1 at xj and equal to 0 at all other points. So here we skip point j, and we have these linear factors, x minus any of the other points. And then down below we have xj minus those same points. Notice here, xk up top, xk down below. That way if we plug in x equal xj, we're going to get 1. So what I'm going to challenge you guys to do is, given these points, let's say x naught is equal to 1, I'll keep it simple, x1 is 2, x2 is equal to 3, x3 is equal to 4. Okay. What are Lagrange polynomials? L0, L1, L2, L3 for these points. And if they're going to be cubic, So however many points you have, the degree is going to be always one less. So for instance, L0 is equal to 1 at x0, and it's equal to at 1, and it's equal to 0 at x equals 2, 3, and 4. So now with specific numbers, now that you know where you want it to be 0, then it tells you what the factorization is going to look like. So anyone want to try rattling it off, starting with the numerator? So first, handle this. How do you describe a polynomial that has roots at 2, 3, and 4? What's the factorization? I know you know that. Take a stab. Yeah, see, just rattle that right off. Okay. Now, this will automatically satisfy these three conditions. You just need to, now, divide it by the right thing. I'll put some parentheses or put some brackets up front to make it sure that if you plug in x equal 1, that this will happen. So what are the factors we put down here? You don't have to simplify them. They can still be, like in this form. It'll be easier to see why it works. And if I refer you, basically it's this that you're trying to, it's like you've done this part already up top, and it's this part down below that you need to fill in. Notice what's similar and different about them. What? Yeah, and we'll fill in the specific value of x naught. Yeah, 1. 1 minus 2. 1 minus 3. 1 minus 4. There it is. So that's Lagrange polynomial that's equal to 1 at the first point, 0 at all other points. Okay. All right. Show me you're catching on. What's the next one? It's equal to 1 at the second point, 0 at the first, third, and fourth points. Yeah, and I'll fill in this particular. Well, not x. Well, x naught, but x naught is equal to 1. Yeah. Yeah. 1, and then x minus 3, x minus 4. Okay. And what goes down here? Don't bother simplifying. What? 2. Yes. 3, 2 minus 4. Okay, so, yeah, so notice whatever you have here as your roots is always the second number. The first number down below is a point where you want it to be equal to 1. Okay. All right, can you crank out the next one? So it's equal to 1 when x is equal to the third point, which is equal to 3. Yep. Over 3, yep. Yeah. Okay, and then this last one should be old hat, right? Yeah. Okay. See, now you guys know a new party trick. Okay. So, okay. Now, so I showed you one way to construct these Lagrange polynomials, like in MATLAB, and you can use polyfit, where your x values are your points, and then your y values are all zeros except for a 1. Another way to do this I'm going to show you how to construct L0 using conv. Conv is for multiplying polynomials. Conv is short for convolution. It happens to be the same operation mathematically. That's why it's called that, instead of something more intuitive for polynomials. So if I start of L0 is equal to 1, let's say, initially, and then I can say L0 equals conv of itself with x minus 2, but that's represented as 1 minus 2. In other words, I'm multiplying, so L0 is equal to L0 times x minus 2, because those are the coefficients, x minus 2. And then I do it again, multiplying by x minus 3, and then again by x minus 4. And then I just need to scale it. But so I can do L0 divided by these numbers down below. So 1 minus 2 times 1 minus 3 times 1 minus 4. And there's my Lagrange polynomial. And what I'll do is I'm going to plot that on the same graph as I already had. In magenta. Okay. And there it is. It's equal to 1 at x equals 1, the first point, and it's equal to 0 at 2, 3, and also over here at 4. Okay, so there's a couple different ways to build up polynomials. Because homework 3, there'll be a function where you make your own Lagrange polynomials and then also implement your own version of polyfit to perform polynomial interpolation. Okay, so so you can use either approach to make the Lagrange polynomials, and so what you can do is okay. So in effect, what I've done here in this graph, in this magenta curve here, this is a polynomial that fits these 4 points: x equal 1, 2, 3, 4, and y is equal to 1 here, and then 0 for the others. But if I have all 4 Lagrange polynomials, I can take linear combinations of these to fit any points that I choose. So back to our quadratic example, we saw I had you construct L0, L1, and L2 back up here. So after making Lagrange, not multipliers, that's a Cal 4 thing, Lagrange polynomials, multiply by y values and add. Now, I showed you this form before, so P2 of x is just going to be y0, L0 plus y1, L1 plus y2, L2. So once you have Lagrange polynomials, after that, it's really easy. Okay, I'm just about out of time, unfortunately, but I will continue with this on Tuesday anyway. But one of the drawbacks is, suppose I needed to change which points I was interpolating at. Like, suppose I wanted to add another point, because maybe I have more data I want to include. Then all of this is kind of useless. I'd have to reconstruct the Lagrange polynomials in their entirety, whereas there's another approach called Newton interpolation using divided differences, where if you want to add a point, it's much easier to update your polynomial. But Lagrange polynomials are going to be very useful to us for designing methods for approximating derivatives and integrals. So we're going to see that when we get to that chapter too. Okay, I sense you guys packing up, and yes, it is 5:05. So we'll continue with this on Tuesday, and be sure to keep questions coming about homework 2 to get that done.